Hello students. In this session, first of all, let's take a quick recap on the periodicity of e raised to z. We had seen in the previous session that the period of e raised to z is 2 pi I n, where n belongs to the set of integers, and the function e raised to z is behaving in the same manner in horizontal strips of length 2 pi, and to be precise, these strips will be minus pi less than or equal to the imaginary part of z less than or equal to pi less than or equal to imaginary part of z less than or equal to 3 pi, minus pi less than or equal to imaginary part of z less than or equal to minus 3 pi, and it is going on like that. Okay, so let's just mark here. This is our origin and this is our pi. This will be our minus pi. This will be 3 pi. This point will be minus 3 pi. Here we'll be having 5 pi, and consequently it is going on like that. So each of the strips which are seen here, you can clearly understand that represents what which is written here. Minus pi less than or equal to imaginary part of z less than or equal to pi will be standing for this green horizontal strip. Pi less than or equal to imaginary part of z less than or equal to 3 pi will be represented by this pink horizontal strip, and so on. So in these horizontal strips, e raised to z will behave in the same manner. Okay, and these horizontal lines can be generally formulated as imaginary part of z is equal to 2 into k minus 1 into pi. There is a little difference there. Here it will be 2 into k minus 1 into pi. That means it is odd, right? So that was what we had concluded in the last session. Now we are moving on to define our new function, which is nothing but logarithmic function. As we are standing here, we will call it log of z. We are standing in complex analysis, so we will call it log of z. So the problem is, how will we define this log of z as an inspiration from a real logarithmic function? So we have basically two ideas. The first idea is about the power series kind of idea. In the real sense, we know that if we are defining f of x to be the natural logarithm of x plus 1 for every x belongs to, it is only defined in this particular domain. Okay, that is equal to x minus x square by 2 plus x cube by 3 minus x raised to 4 by 4 plus etc., or generally it is written as summation n is equal to 1 to infinity minus 1 raised to n plus 1 into x raised to n by n. This is the power series of the logarithmic function, and also note that it is translated or shifted to 1. Okay. That is the translated or shifted logarithmic function, which we define with the use of power series. Okay, so this was our idea 1. So what we are going to do is we'll try to use the idea to define our function in a complex plane. Okay, in the complex analysis. So I'm taking f of z is equal to summation, the same function, same power series. Summation n is equal to 1 to infinity minus 1 raised to n plus 1 into z raised to n by n. Okay. So we are going to check for the convergence of this series. Okay. So suppose if it is convergent, and suppose if the limit n tends to infinity, modulus of an by modulus of an plus 1 exists, then we can say that that is the radius of convergence of the power series by using our earlier proposition which we had done. Okay, so this is equal to limit n tends to infinity, modulus of an will be minus 1 the whole raised to n plus 1 divided by n divided by minus 1 the whole raised to n plus 2 the whole divided by n plus 1, right? And the modulus sign will just absorb the negative nature, minus 1 whole raised to n plus 1 minus 1 the whole raised to n plus 2, and what remains is positive natural numbers, so I can remove the modulus sign and write this is equal to n plus 1 by n, right, which is equal to limit n tends to infinity 1 plus 1 by n. When n tends to infinity, 1 by n tends to 0. That means we have the limit to be 1. That will mean that the radius of convergence of this power series is 1. Right? And that will mean that the power series we just defined like this is only convergent. F of z defined, the power series, is only convergent in mode set strictly less than 1, which is a very small portion. And the power series being convergent in this particular disk, unit disk, the same function will be analytic in this unit disk. But this unit disk is very small, and we'll just skip with this idea. We are not using this idea because the portion in which the function is analytic or the power series, the corresponding power series is convergent is a very small portion. So we are going to think about the next idea. This is a very small domain. So when we are thinking about extensions, we might think about a little more larger domain. Okay. Not using idea 1. So now let's think about idea 2. For idea 2 is closely related to this. Suppose if f of x, this is in the real sense, f of x is equal to log of x, the natural logarithm of x, that is often treated as the integral 1 by t dt from ranging from the lower limit 1 and the upper limit x, where x is strictly greater than 0. This is another possibility. We can use the same definition as we used in the real logarithmic function and treat it in complex. But this is a kind of risky business because we are dealing with integrals and so on. And also that there is one another problem. In the complex analysis case, in complex case, one thing you have to notice, e raised to z is not a single valued function. Single valued function. Or rather, I'll say it is not a one to one function. So, as it is not a one to one function, what which is going to happen is it is not possible, it is often not possible to define a log z like in this idea 2 and then take the inverse function to define log z as the inverse function. Yes, log z as the inverse function of e raised to z. So that is a problem since e raised to z is not a single valued function which we had seen earlier. Why it is not 1 1, rather 1 1. But we are going to use this idea to in some sense when we are going forward. Okay, we had completely withdrawn the idea 1 and now we are going to use some sense in the idea 2 which we described now. So let's see how we will move on. Okay, so let us see what is our basic aim. Our aim is to define logarithm of a complex number w such that the following condition is satisfied. So what is the following condition? That is inspired from idea 2. That is when z is equal to, when a complex number z is equal to log of w, it will imply just an extension as we see in the real sense. If you are taking e power z, e power log w, that will imply e power z is equal to w. This is what which is to be satisfied, right? So this is a basic condition or the requirement we are insisting. Okay, so now we'll see some observations. Okay. We had earlier seen that e raised to z can never be 0 for every set belongs to the set of complex numbers, right? So suppose if our w and z is satisfying the condition which is in the box you can see. Okay. So then e raised to z, which is equal to w, can never be 0, right? For every set belongs to C. Right. Now, therefore, we get something. We cannot take W as 0, and that will imply an important thought, which is log 0 is not defined. Why? Because e raised to z can never be 0, that means w cannot be 0. That means this w cannot be 0, that means log 0 is never defined. That is yet another important basic factor about log z. Now, okay, suppose if we are letting w not equal to 0, and suppose we are assuming that e raised to z is equal to w. Fine? Okay. Now, if normally z is written to be x plus iy, where x is the real part and y is the imaginary part. Okay. Now I am going to take the modulus of w. Modulus of w is nothing but modulus of e raised to z, because we have assumed w is equal to e raised to z. That is equal to modulus of x e raised to x plus iy. And we had seen the property of e raised to x plus iy, it can be written as e raised to x into e raised to iy, right? That is equal to modulus function can be is satisfying this property. Modulus of z1 into z2 is equal to modulus of z1 into modulus of z2. That is the property here. And this is equal to, we had seen the same earlier, e raised to iy is equal to cos y, where y is a real number, plus I sin y. That means modulus of e raised to iy is equal to root of cos square y plus sin square y. Here it is in the real sense. Obviously we know that that is 1, so that is equal to 1. So I can give, instead of modulus of e raised to iy, I can give it as 1, and modulus of e raised to x is nothing but e raised to x, because x is a real number. So this is e raised to x, right? So what did we just got? We got that modulus of w is equal to e raised to x. E raised to x is nothing but e raised to real part of z, right? Now, w is equal to e raised to z. That is equal to e raised to x plus iy, which is equal to e raised to x into e raised to iy. I am calling e raised to x as r, okay, where r is equal to e raised to x. Fine. So I have written the complex number w in the polar form. Okay. In the polar form, r is equal to e raised to x. We got that. But e raised to x, we got it to be modulus of w. Uh, no, I can write it to be e raised to x, right? That is equal to e raised to the real part of z. But we had seen that this is nothing but modulus of e raised to z in the earlier sessions. Okay. So we have that much. Let it remain there. Okay. Now you are thinking about the argument of this w. Okay. Now let's see e raised to z. Okay. E raised to z has period, it is periodic and it is having the period 2 pi I n where n is varying in the set of integers. We just said this in the recap too. Okay. So e raised to z has the PD 2 pi I n will mean that e raised to z plus 2 pi I n will be equal to e raised to z for every z belongs to the set of complex numbers. This is the meaning of e raised to z being periodic with the period 2 pi I n. Fine. So this will necessarily imply I am taking e raised to iy, okay. This e raised to iy can be written as e raised to iy plus 2 pi I n. Instead of this, for every set this is happening. Instead of z, we have just iy, that's it. So this is equal to e raised to I into y plus 2 pi n. This is a gentle observation, okay. So now we can just rewrite our w, okay. We have our w to be equal to r into e raised to iy, right? So instead of e raised to iy, I can substitute e raised to I into y plus 2 pi n, where n is belonging to z, right? Okay. So from this, you're getting something, right? We are getting that argument of w. Argument of w is the one sitting here, the theta. That is equal to y plus 2 pi n, where n is belonging to z, right? So we can rewrite the same to write like this. I'm taking this 2 pi n into the left. So that means you'll have minus 2 pi n, right? But the n is varying in the set of integers. So it doesn't make any difference if I write like this. This is equal to argument of w. You can write it as plus or minus 2 pi n. I am taking it to be 2 pi n itself, where n belongs to z. So this is a gentle conclusion we are getting. So how we will just make everything better. So if e raised to z is equal to w, we started with this. Okay. Then we got at first that modulus of w is equal to e raised to x. This is one observation we just got here. See, modulus of w is equal to e raised to x. Yes, we got that observation. And this one is obviously in the real sense because there is no complex number involved there. Everything is in real, right? Now think about log of mod w. Just think about that. That will be log of e raised to x, right? This is the natural logarithm. That means to the base e, right? This is the real sense. So I can write log of e power x to the base e here, right? So that is nothing but x because this is in the real sense. We know that. So we now got that x is equal to log of mod w. So we obtained something very interesting. Here you got y is equal to a particular factor and x also you got here as log of mod w. Okay. So you're going to just make them together and say what z is. So we started with if e raised to z is equal to w. I'm going to solve this equation. Okay. So that will mean z, which is equal to x plus iy, is equal to log of mod w plus I into, just look what y is, I into argument of w plus 2 pi n, where n is varying in the set of integers. So this is yet another observation we end up with. Okay. Now let's see let's conclude by saying that the solution of the equation e raised to x, e raised to z, e raised to z is equal to w is the set of all complex numbers such that z is equal to x plus iy, where x is equal to log of mod w and y is equal to argument of w plus 2 pi n, where n is varying in the set of natural numbers. So that is a conclusion we get from there. Okay. Now let's see how we will prove preposition 2.19. For that, before moving on to that, we need some basic presumptions. So suppose we are given that G is an open and connected set of complex numbers, and f from G to C is a continuous function. Continuous in the topological sense. That will mean for every open set in C, F inverse of the open set will be an open set in G. Okay. It is a continuous function such that Z is equal to exp of f of z for every set belongs to G. Okay. Now we are going to define what the branch of the logarithm is. Clearly read the statement. We have a G which is open and connected, and I am having an f from this G to C, and it is continuous such that z is equal to the exponential function of f of z for every set belongs to G. Then this f is called the branch of the logarithm. F is called the branch of the logarithm. So this is a very important definition when we study about the logarithmic functions. Okay. So from here, when z is equal to log w, we have e raised to z is equal to w, right? This was a condition when we started to formalize the idea too, right? So here, when we are thinking about the branch of the logarithm, where the branch is the function itself, here we have z is equal to exp of f of z, right? That is equal to e raised to f of z. And we know that the exponential function can never be 0 for every set belongs to C. And here also for here this f of z is a complex number in the complex plane. So this is also not equal to 0. That will mean that you know that the function is happening from G to C, right? So this e raised to f of z can never be 0. That will definitely mean that 0 can never be in G because e raised to f of z is equal to z, right? From where does this set come from? The set is coming from G. So you cannot expect that 0 is in G. 0 is necessarily not in G. Okay. Now we are going to start with our preposition 2.19, and before moving on, I'd like to just state the preposition which says that suppose if we have G subset of C to be open and connected, and you are having f as a branch of log z, you're given the first one, you're given this, okay, log z on G, definitely. Then all branches of log z will be the functions f of z plus 2 pi ki, where k varies in the set of natural numbers. This is our preposition 2.19 talking about. Okay. So we are going to prove this preposition. Let's see how we can prove. There's a very easy proof. Okay. Suppose we are saying we are given everything. We are given that G is open and connected. F is a branch of log z on G, right? So we are firstly defining a new function, okay? A new function g of z. Say it is g of z. This g of z is the type of function we are talking about. F of z plus 2 pi ki for every set belongs to G. Okay, this is a G of Z. Now I am taking e power G of Z. Okay, e power G of Z is nothing but e power f of Z plus 2 pi ki, right? By the property of exponential function, you have this is equal to e raised to f of Z into e raised to 2 pi ki, right? Now you can think about e raised to 2 pi ki, okay, that is equal to cos 2 pi k plus I sine 2 pi k, right? So this is equal to cos 2 pi k for every k belongs to z will be 1 and sine 2 pi k for every k will be 0. That is, this is equal to 1. So I can substitute that here and I get this to be equal to e raised to f of z into 1. But f is a branch of log z. We have assumed it. So branch of log f being a branch, we know that e raised to f of z will be z. So this is equal to z, right? For every z belongs to g. Now you got that e raised to g of z is equal to z. What does that imply? That implies g is a branch of the logarithmic function. This is an observation at first. Okay. Now think about f of z minus g of z. Okay, we have f of z minus g of z. And just think about e raised to f of z minus g of z. Okay, what is that? E raised to f of z minus g of z. You necessarily know this is equal to e raised to f of z into e raised to minus g of z, right? That is equal to e raised to f of z divided by e raised to g of z. These are the properties which we had seen while we were dealing with exponential functions. Okay. And both being branches of logarithmic function, you get both of them to be z. And z is never 0, so you can cancel out and you get it to be 1. Okay. Now what you obtained is e raised to f of z minus g of z is equal to 1. Okay. This will happen if and only if f of z minus g of z is of the form which we just saw now. See here, e raised to 2 pi ki is equal to 1. This is the only possibility when e raised to something is equal to 1. Okay. That will mean that f of z minus g of z is equal to 2 pi I k, where k is coming from the set of integers. Fine. Now you're going to define a new function h of z. Let this h of z be equal to 1 by 2 pi I into f of z minus g of z. Fine? Okay. Here f of z and g of z, f of z you already know that it is a branch. So definitely it is a continuous function by the definition of branch. G of z you defined as f of z plus something, right? Plus a constant. G of z is equal to f of z plus a constant, and that is also definitely a continuous function. So f of z minus g of z is in turn a continuous function, and that function divided by a constant is also a continuous function. So here h is necessarily continuous. Continuous. Okay. And what is it equal to? 1 by 2 pi I. This is equal to f of, what did we obtain earlier? We obtained that f of z minus g of z is equal to 2 pi I k, right? So I can, instead of this f of z, I am going to substitute what we got from here. So I can substitute it to be g of z, let me call it hash. Okay, from hash, I am going to substitute f of z to be g of z plus 2 pi I k minus g of z. Okay. So they cancel out, and what you get is 2 pi I k divided by 2 pi I, that is equal to k, where k is varying in z, right? So that implies the image of this function h is always an integer, right? So you're getting something like this. H when applied on G, Z is coming definitely from G, will lie inside the set of natural numbers. Sorry, set of integers, right? Now, you have some observation to make. Now, G is a connected set as we had taken in the hypothesis, and H is a continuous function in the topological sense. That will imply H of G is a connected set. This is a property of topological property which says that connectedness is preserved under continuous function. Okay, G is connected and H is continuous will imply H of G is connected. So what does that mean? To be very specific, H of G will be nothing but the singleton's set G, singleton set case, because here H of G has to be connected. Note that if you are thinking about the integers, integers will be like this 1 3 minus 1 minus 2 minus 3, like that. They are not connected with each other, and here it is said that this h of g is inside these set of integers, but this h of g is connected. So the only possibility of h of g is to become a singleton set inside this set of integers, for that to remain, so that it is equal, so that it is remaining connected. That is the only possibility. Okay, which means the fixed k. So we are fixing a k here because it can be only a singleton set. The fixed k will work for every set belongs to G. Okay, that is simply saying that f of z is equal to g of z plus 2k pi I, right? For every set belongs to the set G, the open connected set G. And the particular k will work for every set belongs to G. This is what we finally conclude. Okay. So before moving on, we can just let it remain in that way. So this is what we are ending up with, and let's just see the preposition. The preposition said like this: we are given f to be a branch and all branches of log set will be functions like this. Okay, we are getting the k to be from the set of integers, and the k is fixed, and we get that the functions are like this. The branches of log set will happen to be like this. So we are ending up I want this. Let it remain like this, right? So, thank you. See you in the next session. So, bye.